All right, guys, the time right now is 3:35 when I'm starting this video, which officially means I'm off the clock. I'm basically working for free. My contract says I only have to stay on campus till 3:30, but I'm putting in the work for the people who want to do better. That's what it comes down to. You saw all those things I was posting on Remind today. Even if you just think back to August, if you were in my class in August, I told you, I'm going to be the best teacher you ever had. And the only way I can do that is by doing things that other people are not willing to do. So, I mean, just think about it. I'm working for free right now. I don't get paid overtime for this. And I'm about to do this entire review so that you can take advantage and not have an excuse to fail tomorrow. So I'm going to go through the review. I'm going to do every single problem. Now, when I say I'm going to do every single problem, I may not reduce and I may not finish the math, because if it's something in the calculator, that's up to you. And so, guys, yes, I want you to learn the math, but there's bigger things I want you to learn from being in my class. And so one of the things is work hard and good things will happen. Now, if at the end of the day you look back and you said, I've done everything I can, well, then you should sleep good at night, because that's how I approach my life. At the end of the day, I know that you guys, when you were sitting in my classroom, you got the best version of me that I could possibly put together for you. So if you live your life like that, you can't fail. Okay, so probability. When you do probability, you got to basically make a fraction. So number one, a jar contains 6 green marbles, 4 yellow marbles, and 5 orange marbles. What's the probability of selecting an orange marble? Basic probability. Total goes on the bottom. There's 15 marbles altogether, and you want to pick the orange marble. Probability of picking orange, top number, is how many favorable outcomes there are. So that's 5. And then you can reduce that yourself. So type in the calculator and see what you get. Number 2, if Emilio tosses a number cube is just die 30 times and gets 6 12 times, he concludes that the probability of getting a 6 is 40%. Is this theoretical probability or experimental probability? Explain your answer. So this right here, you got to know the difference between theoretical and experimental. Theoretical is what's supposed to happen, and experimental is what happened after you did the experiment. So right here where it says he did it 30 times, guys, those are trials. So that automatically makes this experimental. If you do the experiment and you run trials, that's automatically experimental. Now, if this was theoretical, doesn't matter. Like, the number of times doesn't matter because you don't do the experiment. You just say you have a 6-sided number die or a number cube, whatever they call it. And so the probability of any number is 1 out of 6. So the number of trials doesn't affect the probability at all. So that's the big difference. Number 3, a single card is randomly selected out of a standard 52 deck of cards. Are the events selecting a face card? So here's event number 1, selecting a face card. And then here's the key word, and. Selecting a diamond, mutually exclusive. Okay, so this question about mutually exclusive. So first of all, you should have said or. So I think that's a typo. But we're going to pretend it says or, and we're just going to take a look at it. So what is a face card? A face card is anything that has a face on it. It's pretty self-explanatory. So here's all my face cards. There's 12 of them. Then we go and take a look at the diamonds. So here's the diamonds. There's 13 diamonds altogether. So when you want mutually exclusive, you don't want your groups to intersect each other. So if you have any overlap, which in this case we do, that's not mutually exclusive. So right here, we have some sharing that's going on. When we count the 12 face cards, those 3 cards get counted. And when we count the 13 diamonds card, those 3 same cards get counted a second time. So that is not mutually exclusive. So the answer is no. Why? Because the 2 events, I'm going to say they intersect. Intersect is the word that they use for the overlap or the double counting. So the next one says, what's the probability of selecting a face card or a diamond? So here's the actual probability. Face card, there's 12 of them out of the 52. Diamond, there's 13 of them out of the 52. How many overlap? There's 3. So we have to subtract the 3 because they got counted once in the 12 face cards and once in the 13 diamonds. So we subtract that part, we add these together, you can type it in the calculator and finish that. Number 5, from a standard deck of 52 cards, find the probability that you draw a heart on the first draw, and is our keyword that tells us we're going to have to multiply, a diamond on the second draw without replacing. So right there, that's a dependent event. So a dependent event means you have two probabilities that have to be multiplied. There's 52 cards in the deck. You can only pick one. It says, I know it says you're going to pick 2 cards, but you're going to only pick one at a time. So that means the second time, since you didn't put it back, there's only 51 cards. What are we trying to pick? A heart? There's 13 hearts. And then the second time we want to pick a diamond. There's 13 diamonds. You do the math. You can type that in yourself. It says, are the events listed above independent? The answer is no, they're not independent. Here's why. See that number right there? It started off as 52. Then it went down to 51. So since we didn't replace it, that's a dependent event because the second event was affected by what we did with the first after the first event. We didn't put the card back. So that basically changes your probability because it changes the bottom number. Okay, number 7, you're randomly selecting one number from the numbers 1 through 30 inclusive. So it means including 1 and 30. What's the probability that the number is less than or equal to 12 is chosen? So less than or equal to 12 means 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's 12 numbers out of the 30. So you can simplify that in your calculator. Number 8, use the following graph about volunteer age group to answer the following question, 100 volunteers were surveyed. Bam! That part right there is important because that's your total. So you already know the bottom number is 100. It says, what's the probability that a person selected at random is at least, there's that keyword we talked about in class, at least 40 years old or older. So you got to think of the amusement park. If it says you have to be at least 40, you can't be under 40, you can be exactly 40, and you can be higher than 40. So any category that's 40 or higher needs to be counted. So basically it's this one, this one, this one, and this one. You guys can add those up yourself and put that number right here. And then you reduce it. Okay, the next one. It says the result of rolling a fair 6-sided die 80 times. Bam! There's your total. 80 times. That's your bottom number. And it says to find the experimental probability for each number on the die. Experimental probability. 80 times. That's how many times we're rolling this. So every single one of these is going to be 80 at the bottom unless you have to reduce it. So if you want to find the probability, what you do is you put the frequency on top. The frequency means how many times it came up. So for example, the number 1 came up 11 times. So 11 out of 80. The number 2 came up 13 times. Number 3 came up 9 times. 4 came up 17 times. 5 came up 16 times. And 6 came up 14 times. You can type those in the calculator to see if they're reduced. What's the theoretical probability? So we don't have to know how many times we rolled because theoretical probability is what's supposed to happen. This dice is numbered from 1 to 6. What's the probability of getting 1? 1 out of 6. 2? 1 out of 6. 3? 1 out of 6. I think you get the point. Every single number has a 1 in 6 chance of coming up. So the experiment above doesn't impact the answers at all because this is what's supposed to happen. Next, if you flip a fair coin 60 times, what is the expected number of heads? So if you want to calculate the expected number, your expected number is figuring out the number of times and multiplying it by the probability of the event occurring. So we're doing it 60 times. We're going to multiply that by the probability of flipping heads. It's 1 out of 2. So our expected value should come up 30 times. Now, is that what really happens? Who knows? It's different every time we do it 60 times. But according to the law of large numbers, if we were to do this 1,000,000 times, it should come up half the time. Okay? Next question. Find the probability of A or B. If probability of A is 75, probability of B is 0.5, and the AND is 0.4. So, number 1, you got to know which formula to use. It says or. Or is a plus formula. Number two, you should be able to look at this and automatically know if it's mutually exclusive or not. And where do you find that? You find it right here. If that number is 0, it's mutually exclusive. If it's any number besides 0, it's not mutually exclusive. So if we're going to use the probability formula, it says A or B probability is the same as probability of A added to the probability of B minus the probability of A and B at the same time. Substitution, guys, plug the numbers in. 0.75 plus 0.5. Now, if you just did that part, that's already over 1.0. So you should know, again, that doesn't make sense. Probability is always in between 0 and 1. So then we subtract 0.4. You do the math. You can type that in yourself. Okay, number 13. Probability of A is 0.6. Probability of B is 0.3. Probability of A and B is 0.1. And it says, as shown in the following diagram. Guys, they gave us the numbers. We don't need the diagram. I mean, you could use it if you want to, but we don't need it because they gave us the numbers right here. A, B, N. So the question is, what's the probability of A and B? So guys, you want to find the probability of A given that B has occurred? The only way you can do that is by multiplying it to the probability. So we talked about this in class. These formulas alternate. So if I have an A and then a B, they need to alternate. So this would have to be a B. That should give us the answer to A and B. So now it's straight up substitution. A and B is 0.1. Probability of B is 0.3. Probability of A is trash. We don't need that at all. And then we multiply that by the probability of A given that B has occurred. Now, if we want to solve for the probability of A given that B has occurred, divide by 0.3. There's only two things that could happen. Either the numbers are side by side where you multiply, or they're on different sides. So then you would have to divide, so you end up with 0.33 for the probability of A given that B has happened. Okay, next one says, if events A and B are independent, so first, what the heck does independent means? Independent means one does not affect the other. So I mean, explain how probability of A compares to A given that B has occurred. Well, guys, if you did, just think about it. If A has no effect on B and vice versa, then it doesn't matter that B has happened. So basically, the probability of A given B is the same as this. It's the same as just the probability of A. So if they're independent, the probability of A is exactly equal to the probability of A given that B has occurred. Because B doesn't impact A. Because in the first part of the sentence, it says they're independent. Okay, next. Number 15. Probability of A equals 0.3. Probability of B is that. 0.6. Probability A or B is 0.7. So they're asking, are they mutually exclusive? So guys, if they're mutually exclusive, here's what happens. Probability of A or B should equal probability of A plus probability of B. If two things are mutually exclusive, we don't need the subtraction part because that part equals 0. So basically, we just test it. So A or B is 0.7. Probability of A is 0.3. Probability of B is 0.6. Do these add up and equal each other? That's the question. So we end up with 0.9 equals 0.7. So the answer is no. They're not mutually exclusive. If they were, they would have added up. So that means there's a subtraction part to this. So anytime you have the subtraction part, that means that they are not mutually exclusive. So the answer is no. Bam. Okay, the next one. The next one is a dependent event. You can tell because the formula for dependent has these given lines to them. So this is another one of those ones we've got to figure out which one we need to use. So let's see what we have here. We have probability of A and B. So guys, we got to think about this. When we look at these probabilities on the formula sheet, the very first page, there's only two options. There's a second option right here where it says B and then probability of A given B. They're alternating. We only show you one because the other one is basically the alternate version. So, I mean, if you think about it, you have to have the two numbers next to each other because they told us to find this. We don't know what that is. So obviously, we have to have the numbers on the right side. So looking at it, we either have to know the probability of A or the probability of B, because I know for a fact they gave me these two. They gave me the two givens. So now we just got to go back and check if they gave us A or B, because that will determine which one we need. So let's go back down. Probability of A and B. So they gave us A. We have to use A. And that means if we're using A, they have to alternate. So B is next, and then A. So plugging the stuff in, this basically means that AB is trash. We don't need that. So probability of A is 0.6 times the probability of B given A, that's 0.3. I think that's probably like 0.18 or something like that. Okay, decoding. We have to decode these problems. Now, you got to read carefully because this is all about using the right information. There's going to be information in there that you don't need sometimes. The way I showed you how to do this in class is go to the last sentence and decide what's the A event and the B event. So, throws the ball to Pluto. That's A. Pluto drops the ball. That's B. So it says Donald, the quarterback. Actually, that should be one word. That doesn't make any sense. Anyways, he has two wide receivers, Goofy and Pluto. I don't care about Goofy. The question is about Pluto. So it says the probability that Donald throws to Goofy is 0.60. Look at my last sentence. That's not event A or B. A is throwing to Pluto. B is Pluto dropping the ball. So I care less about that sentence. Okay, next. The probability that Goofy drops the ball. Again, I don't care about Goofy. I mean, I like the character, but I don't care about him in this problem. Donald throws to Pluto 40% of the time, or 0.4. So the probability of throwing to Pluto, oh, no, it's on the board, is 0.40 is just 0.4, whatever. The probability that Pluto drops the ball is 0.30. Probability that he drops the ball is 0.3. Find the probability that Donald throws the ball to Pluto and he drops the ball. So guys, they want us to find this, A and B. So if you look back at the formulas, there's only one that has an and only has A and B. There's no given stuff, so we don't have to use any of this. So we have to use this formula. That means they're independent events. So we just have to multiply the two decimals together. See what we got here. A and B. So it's 0.4 times 0.3. So it's 0.12. Okay, from a table. So when you're doing probability, the only time you do not use the grand total is if it says given. So I don't see the word given in this number 18, so it's out of 310. It says, what's the probability that the reader's favorite is good kind? And forgive me if I say these names wrong, but I don't really care. So I just need to know it's this one. So I need the total. So you put 70 on top. You can reduce that yourself. 7 over 31, I think. Okay, next one. It says, what's the probability they're young adult? Given. Bam, there's your given. So given means, here's what it means. So when it says given, we need to find the intersection between the events that are on each side of given. So we want young intersecting with Asimov. Oh, well, I'm not going to fix that. Okay? So we want that, and we want to add that to young intersecting with Brooks. Then at the bottom, we want the bottom of the stuff that comes after given. So to the right of given, it says Asimov and Brooks. So we're doing Asimov plus Brooks. So if I go up to the table, hopefully my highlighter works, I want the intersection between, where am I? Asimov and young adult. So here's young adult. Bam. Here's Asimov. Bam. There's the intersection. The intersection is at 25. So the top is going to be 25 plus, because we want both intersections. So I'm going to do, let's see, who's next? young adults. I already have that one highlighted. And then the second one is Brooks. Bam. There's our other intersection. So we add that to the top. Then for the bottom, we do the total of Asimov and Brooks. So the totals are down here, 50 and 30. So we do 50 plus 30. And like I said before, guys, you always use the grand total unless it says given. So you can do the math on that one. Next one. What is the probability that the reader's favorite author is Asimov? So grand total, 310. Asimov, 50. And you can reduce that yourself. Next question. Reader's favorite is rolling, given young adult. So again, the formula for this is the intersection between the two events. So it's the intersection of rolling and young, and then the total. And I always mark off given, because to the right is what needs to go on the bottom, the total young adults. So intersection of rolling and young. Get rid of this. Here's rolling, bam. And then the, come on, you want to do that. Go back up. Young, bam. So the intersection is 10. So the top number is 10. Total young, we're doing total young adults, that's 110. Those on the bottom. There's your answer. Okay, the next one, what's the probability that the reader's favorite is Herbert, or means plus, or the reader is older? Okay, so we got to do Herbert, and we got to do that they're older. So I'm going to highlight these. Hold on a second. Actually, I'm going to do this. This is always over the grand total, so it's 310. So we got to do the total Herbert, total older, and we got to see if they intersect each other. So we're doing Herbert, bam, older, bam. So on top, we need the total Herberts and the total older. So it's 100 plus 120, 100 plus 120. And then we go back and look to see if they intersect each other, which they do right here at 50. So that means we have to subtract 50 from this, and then you can do the math. What's the probability that a reader's favorite is good kind, given they're younger than 41? So guys, younger than 41 means a couple of different categories. So younger than 41 means young adult and teen. So again, given means the intersection of good kind, and I forgot what the categories were. Good kind would be young adult, added to the intersection of good, kind, and I'm just abbreviating good, and teen. And the bottom is the total of everything after the word given. So basically younger than 41. So that means young, total young added to teen. So let's see, I'm going to highlight. I need good kind. What was the other one? I forgot. So this is good kind, given that they are younger than 41, so I need to highlight the other way. Younger than 41 means this one and this one. So the overlap, those are the worst colors I could have used. Hang on a second, I want to redo that one. So I'll probably not use purple. That was a stupid example. So we get good kind is this one. I'll do yellow. No, I'll do green. So we're doing this one. So we've got the 15, and we also have the 25. So we got to add those up. The intersection between good and young, good and teen. I forgot what the numbers were. Let me circle them. Here's the overlap. So we have to add those together. 15 plus 25. And then we want the totals of the young and the teens. So that would be here and here. So we have to add 80 and the 110. And I don't care what order you put them in, because it's commutative. Adds up to the same thing anyways. You can do that math. I'm not going to do that. What's the probability the reader's favorite is Brooks and? So and in these pictures means the intersection. So we need the grand total. The grand total was 310. We got to go see where Brooks and Older intersect each other. Get rid of this mess. So Brooks and Older, bam. The intersection is 10. Okay, what's the probability that the reader's favorite is good kind and the reader is young adult? And is the intersection again. So this is out of 310. We got to go see where good kind and young adult cross each other. Good kind, young adult. Oh gosh, I hate when it does that. Good kind, bam. Young adult, bam. They cross each other at 25. So it's 25 on top. And then you can reduce that yourself. Okay, next one. Use also, this is more review. Use the following table, about 20 spins. That's good to know. That's the total of a fair spinner, numbered 1 to 4, to answer the questions. Theoretical probability of getting a 1. So in theoretical, we don't need the table. There's a number, what is this, a spinner, numbered from 1 to 4. There's 1 out of 4 chance of getting it. Theoretical, getting a 2, still 1 out of 4. Experimental, this is where the table comes in. We rolled 20 times. We're looking at how many times we got a 2. It's 6. Reduce that yourself. Experimental comes from the table. We have 20 spins. How many of them are even? Evens are all of these, a 2, and all of these, the 4s. So there's 7 of them all together. Okay, next one. It's got decimals. So that means those are the actual probabilities. So if we want to calculate the probabilities, we just got to see what we need to add up. So probability that x is bigger than or equal to 2. So here's 2. So equal to 2 means count this, and then bigger than 2 is anything this way. So count this, this, and this, and add them up. I'm just going to write that. 0.1 plus 0.2 plus 0.35 plus 0.3. You add it up yourself. You got calculators. Okay, next one. Guys, I have so many questions. What does this mean? Look at what it looks like it means. X is in between 2 and 4. Now it has the equal sign, and that's important because that means you actually count that one. So between 2 and 4 is from 2 to 4 and everything in between. So we add this, this, and this. 0.1 plus 0.2 plus 0.35. You add it up yourself. What's the probability of less than 3? So guys, notice this one does not have the equal to. So it doesn't mean count the 3's, it means count less than 3. So that's from here on. So we count this one and this one. So it's 0.1 plus 0.05. Add that up yourself. You're randomly selecting one number from the numbers 11 through 20, inclusive. That means including 11 and 20. What's the probability that a prime number? The heck? What's a prime number? So guys, here's the difference between prime and not prime. So a prime is a transformer. No, I'm just kidding. That was stupid. It's getting late. I'm hungry. I got to get out of here. Okay. So a prime number is something whose factors are 1 times itself. And that's its only factor. So for example, 11. 11 is a prime because the only way to get to 11 is 1 times 11. 12 is not a prime because you can do 1 times 12. You can do 2 times 6. You can do 3 times 4. So that's definitely not a prime. It's got a lot of different options. So how many numbers are there from 11 to 20? Count them. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now you didn't see that, but I was using my fingers. Oh, got it. It's 10 fingers. I don't have 20 fingers. So 10 goes on the bottom. How many of them are prime? 11 is prime. 13 is prime. Now I'm careful. Don't tell me that primes are only odds because 15 is a prime. 17 is prime. 19 is prime. That's 4. 4 out of 10. Reduce it. 2/5. Okay, fill in the missing information. This is an OR problem. OR means add. So I have to add. So if I want to find the probability of A or B, probability of A or B, I have to add each individual probability together and then subtract the intersection, A and B, if they can give it to me. Yeah, they do. So right there, it's not mutually exclusive. So A is 0.4, B is 0.7, and then the AND is 0.3. That'll give you the OR. Add that up yourself. Okay, it's another OR problem. Same exact formula. This part right here, it says it's mutually exclusive, so we don't even need the subtraction part. So probability of A or B is 0.7. And guys, I'm just using this formula again. It's the same formula because it says OR. So the probability is 0.7. Probability of A. Oh, I don't need that. I need the numbers. 0.5 plus. I don't know what this is. And then if you want, I mean, you could put in -0, but -0 doesn't do anything, so you can just get rid of it. So if you want to subtract that, subtract 0.5. I mean, if you want to solve it, not subtract it. So 0.2, probability of B equals 0.2. Okay, next one. These are all ORs. This is easy. So these have to add up. So again, same formula. I'm using this formula right here. A or B is 0.6 equals probability of A, don't know it, plus the probability of B, 0.5. Take away probability of A and B, so it's 0.3. So guys, simplify that. That's 0.2. Probability of A equals 0.6. So if I want to solve that, just subtract 0.2. Probability of A equals 0.4. Okay, last on this page, I don't know if there's more, but it's got the lines down. They want us to find the and. So we got to see what we have. There's the one probability that's only one letter, so we have to use that one. And then we have to use the one that alternates with it. So if I'm using the I hate this board, that spot. Probability of A, I have to use probability of B such that, or given that A has occurred. I have to use those two. So this one right here is trash. We don't need that. And here's the and part, probability of A and B. Substitution. Do I know A and B? No, that's what we're trying to find. A is 0.4. B, given that A has occurred, is 0.5. So the answer is 0.2. Okay, same thing. It's got lines. Here's the lines right here. It says probability of A is 0.23. Probability of A given that B is 0.27. Are they independent? That's based off of that earlier answer. If they were independent of each other, these numbers would have been exactly the same. So since they're different, no, they're not independent. That means that B impacted A. A was 0.23 by itself, and then when you did B, then it changed to 0.27. What's the mathematical test for mutually exclusive? Mutually exclusive means that there's no intersection. So it's this one. If A and B are independent, oh, that's easy. If they're independent, back to the formulas in the front. Independent. This is for when they're independent. This is when they're dependent. So we just multiply the two together. Oh, God, there's all the answers. So we multiply the two together. Probability of A times probability of B. So times, it's 0.3 times 0.7 is 0.21. Find the probability you draw a 2 on the first draw and a king on the second draw without replacing. Bam, that's dependent. So that automatically means 52 cards. Second time, 51 cards. Draw a 2. How many 2s are there? There's 4 2s. Then draw a king. Draw a king. There's 4 kings. We don't have to worry about mutually exclusive because that's only for adding. So you multiply those. Do that in your calculator. What's the probability the teacher's popular? If it's me, it's 100%. Just kidding. Probability popular. We need total. Grand total is 60. Popular teacher. Popular. How many are popular? There's 40 popular. Bam, 40 out of 60. Reduce that yourself. What's the probability the teacher is popular? There's given. So we need popular intersecting with not effective. Also need effective. So popular and not effective, that's the intersection. And then the total that are not effective. Not effective. I'm going to abbreviate. So popular, I'm going to highlight again. Popular, this one, not effective. This one. So to find the probability, it's the intersection. 10 goes on top. For the bottom, we need the total of people that are not effective. 15. Based upon this table, is the teacher's popularity independent of their effectiveness? So on this one, you've got two outcomes here. And so what you need to test is the probability that they're popular. And then we could just test anyone, I don't care. Popular given effective. So the probability that they're popular, we already found that out. It's 40 out of 60, so that's like 0.666666667. 2/3 is that answer. So if we're going to do, looks like purple, that's the given line. So popular and effective, the intersection of popular and effective. Here's popular, here's effective. It's 30, so the intersection is 30. So the top number would be 30 over the total effective. So again, when you have the given line, anything to the right becomes the denominator, and you need the total of that. So for the effective, total effectives, there's 45. 45. So if you reduce that by 15, you get 2/3 again, and it's exactly 6666667, just like the last one. So are they independent? Yes. They're the same exact thing. One did not affect the other. So being popular is the same as being popular and effective. So it didn't matter. If you flip a coin 30 times, what is the expected number of heads? Oh, I said 50. I meant 30. So if you do it 30 times, and your probability of getting or flipping the outcome heads, half of that. So it's 15 is the expected outcome. And I think, guys, that was the last one. So there you have it. I've done everything that I can do at my end. Now it's up to you. So test is going to be tomorrow. It's a Wednesday. It's a late start. I'm going to show up. So guys, again, my contract says I don't have to be here till 7:30. Tomorrow I'm going to show up at 6:30. So I'm going to be in my room from 6:30 to 7:30 if you want help. Then I have to go to meetings from 7:30 to 8:30. Then I'll be back in my room from 8:30 to 9 if you need help. You don't like me? Go to the Cardinals Nest. They're open from 7 to 9. Now, I know what you're thinking. Mr. Parra, it's too early. Well, guys, sometimes if you want to be successful, you got to be willing to do things that other people will not do. And so, again, I'm doing it for free, showing up at 6:30 for you. So take advantage. I'll see you tomorrow.